Good morning to one and all. Today we are going to discuss about logical equivalence and the laws of logic. So before that we have to discuss what is equivalence. Here if you are taking a two proposition, one proposition is it as a U and another one V, are said to be logically equivalent. So when you are going to tell whether it is logically equivalent, in the sense when both truth value is equal, then only you are going to tell that is it logically equivalent. For example, observe here P implies Q and negation P. So this I can totally conclude it as a U and negation P I totally conclude it as a V. So you just observe this U truth table 1, 1, 0, 1. Okay, this is V. So once I check truth table here 1, 1, 0 up to here it is same, but here it is 1. So in a sense, so both two truth values are not at all equal, then it is not at all equivalent or it is not logically equivalent. You observe this example, I conclude it as a X. So this input, this truth value and this truth value both are belongs to same. Can I conclude these two values, truth values are equal, then these two are logically equivalent. So in the definition he clearly says that the two proposition U and V are said to be logically equivalent whenever U and V have the same truth value, or equivalently the biconditional U biconditional V is a tautology. In a sense, UV's truth value also all truth values are belongs to 1, V all belongs to 1, then tautology is nothing but all the truth values should be 1. So then only we call it as it is a logically equivalent. The symbol of logical equivalent we written like this manner. If you write one dash, one arrow mark, we conclude it as a biconditional. So two arrow mark, one dash, we conclude it as a biconditional. So two dashes. So then we call it as this we call it as a logically equivalent. This symbol we call it as a logically equivalent. Okay. For this example, we tell that it is not at all logically equivalent. For this symbol, we write like this manner. One rough data means over of this we cut it. So then we call it as a U is not logically equivalent to V, like this. Consider this example. Let X be a specified positive integer. Consider the following positions. So okay, in the given example he given P is equal to X is an odd integer, Q X is not divisible by 2. He is asking that whether this P and Q both are logically equivalent or not. You just observe here P is an odd number. Okay, odd number in the sense 1, 3, 5, 7, 9. So that's why we call it is a odd number. Correct, right? And next you observed here Q X is not divisible by 2. So Q X is not divisible by 2 in the sense 1 divided by 2, okay, 2 divided by 2, is it correct? Not at all correct, because he clearly says that the values you are going to take, it is unable to divide by 2. So in the sense you are unable to take 2, but you can able to take 3, because 3 is not divided by 2. Correct, right? Like this, if you consider 1 is also not divisible by 2, 3 is also not divisible by 2, 4 is divisible by 2. That's why you are not taking as a 4. 5 is divisible by 2. Is it divisible by 2? Not at all divisible by 2. That's why 5 also you are going to take. If you go for 6, 6 is not divisible by 2. But 7 is divisible by 2. It's not divisible by 2, correct. 8 is divisible by 2, correct. It is divisible by 2. 9 is not divisible by 2. You just observe the truth value of this P as well as this Q. Both truth values comes, means in the sense output comes same. It is also odd number, Q is also odd number. That's why P or Q are logical equivalent is asking. Okay, we note that P and Q have the same truth values. You observed here the same truth value. As such, P or Q are logically equivalent. That is P logically equivalent to Q. So we written like this manner. So once he given the proposition, in the sense that time you check like this manner. Okay, if he is asking using a truth values or truth table, we have to solve this one. For any two proposition P and Q, prove that P implies Q is logically equivalent to negation P disjunction Q. Negation P disjunction Q. Fine. So for any two proposition P and Q, prove that P implies Q is logically equivalent to negation P disjunction Q. Correct, right? I written this truth table P, Q as well as. What is P implies Q? 0 implies 0, the output is 0. 0 implies 1, output is 1. 0 implies 0, output is 1. 1 implies 0, output is 0. 1 implies 1, output is 1. So this is our output. Correct, right? Negation P. For that purpose, here I am taking negation P. So P is 0. Then output is here is 1. Here P is 0. Output is 1. Here P is 1. Output is 0. Here P is 1. Output is 0. Correct, right? You just do disjunction. Negation P, disjunction Q. So 1 comma 0. 1 disjunction 0, output is 1. Any one input belongs to 1 in disjunction, definitely the output is 1. 1 comma 1 in disjunction is 1. 0 comma 0, the disjunction output is 0. Correct, right? Here 0 comma 1, disjunction output is 1. You just observe P implies Q is logically equivalent to P disjunction Q. You observed all truth values 1 comma 1, correct. 1, 1. Here also 0, here also 0. Here also 1, here also 1. So definitely you have got the same thing. There is no difference truth value. So that's why we easily says that it is logically equivalent. Equivalent. It is logically equivalent. Correct, right? Fine. We go for the next example. Prove that R implies S okay, it is for the example of check whether it is a tautology. Forgot. Next we have go for first for whether it is logical equivalent or not. These questions we go for here. Prove that for any proposition P and Q, the compound proposition P by exclusive disjunction Q and P disjunction Q conjunction negation P disjunction, negation